Hello, good morning. So we'll keep compare our CSCI for 52 is a memory analysis. And today will be much more focused on the lecture part. So, but if you still have any question about your assignment, you can ask me by the end of the lecture. Okay. So slightly just recap what we did cover about our last lecture. So we mainly focus on about our Windows like 32-bit system. So we mainly know that if we have the high level language and then the compiler, so they will compile those like source code to machine code, and then maybe once they compile to it, we use some like malware which will be executable. Those will be the you see the binaries like this, and then they will when they convert to the lower level language, so they will add it to those like this assembler and then through it, and then you see. And we try to talk about if we have like different operands like for those register files, like including we take an example like move, so from different source to destination, so including the register, some memory, or immediately. Okay, so we have several way for to specific the address of the data. So including actually indirect, or sometimes including the base with the displacement or index and the scale index. So here will be the memory addressing mode we need to know. And that's what we start by. And then we will try to continue. Like if we by the end we have L by the end. Okay, you see move, right? Move, the one command will stand for long and it represents 32 bits. And for the size of the it shows the size of the operand, and then the page for the days of the 16-bit processor. Okay, so it's pretty long time ago. And you will see maybe for 32-bit or like for later move on like 86, 64. So they will have different words. Like if for 8 bits will be bytes, and then will be move B, and then for the word will be like move with a word, or the double or long 32-bit, so with a move L. And if for the 64-bit, then we'll use the move Q, so code word. Okay, so just the same idea, the logic. If nowadays, if you working on the 64-bit, then it should be the move Q. Okay, and we have some global variables and local variables if you're waiting. So if you remember, we sometimes look at our some files, right? If you remember, so we try to check what's the .data or .bass. So those like global variable. So they will start either if for the initialization, if they are initialized, so in .data, okay. Also maybe some there in a section of like an initialized, so with .bass, okay. So we within this, and for the local variable. So what is the local variable? That means the functions like we declare inside using inside the function, we call it the local variables. They will store on the stack. Okay, so that's how we label the location of the variables in this code. So for the global, then we know like right here. So we expect it to see E equal to 7 should be like belongs to the data, and then for the local variables right here, it should contain stored on the stack. So it will be like this. Then right here, when we look at this, then we need to check. Okay, so if we have the global variables and then some local variables, say right here, and if you see with the push, okay, maybe we have the register, and then we move from the EBB to ESP, and then we substitute the value like this, and keep on, we just like moving okay, from different registers and add them together and move it, go back and leave, right? So like this. And if it's inside the function, you see we try to push the value and move, and then we try to subtract it and move again. Okay. And we try to compare it's larger or equal to, like this. And then we'll try to move it to another register, like from the memory register to another memory, and then move it. So you look, check the two both line, which is like pretty similar. So you start to distinct. And then one more things, we will load the effective address. So like this, and we will loading address, we will getting the actual address to this value. So we will load the address of the S. So in D right here, so like this, but not the content. So if you know the one, with the if we are writing in C, we're using the address the extra D and then represent. So this one would be the memory address. And we also use it to compute the address without the memory reference. Okay, references. And the destination, they must be the register. So here's like we need to be careful. And commonly they use that by the compiler to do some simple arithmetic. So for calculation. So for the leaf, L will be represented as long, as what we say. So we move it from the register, okay, the address of this, and then put it to the X. So it kind of like similar equivalent. So if we moving it, move L, or maybe we use in the C. So the format like we try to get the address of the array location and save to P. Kind of similar. And for the arithmetic operations right here, so inside a function, if we assign it, let's say if we have the 0 to A, and then B equals to 1, and then A will plus 11, or A minus B, and then A minus or B minus. So right here you see just like refer to the machine code or like the assembly code. So we try to add the value to the but we initialize with the 0. So you see just like the register is just empty, and also we try to subtract the location, and then we'll move it the value, and then by adding it to values, or sometimes like if we for minus, we will subtract it and minus or add it back as 1. So we refer to the location. And for the condition code, so we have the i32 processor. So we have the register called the effect. So it's called the extended flag. So for each bit, they is a flag. So or some like condition code. So if you see we have some kind of carry flag or the sign flag or like zero flag or the OF, the overflow flag. So right here. So we are not writing anything like to this register or set them with it directly. So those are like only for the if you know or this flag is for let's say for addition, subtraction, and we'll carry one more bit, so that we are using it. So those flags are set or claimed by the hardware on each like arithmetic or logical operation. So it depends on the result. And those like conditional branches will be handled like through the effects. So that's how it. And if we are setting like those like condition code, like by compare those like instruction. So if we compare like minus it, so we without like setting a destination. Okay. So if we have the curve, then it's set. So if I create out the most significant bit, okay, maybe we are using for some unsigned conversion or a seal flag. Okay, if they are set, if they're equals, or you see right here, if we have some unsigned one, So we'll check it. Okay, if we come at -0, so we have a side flag and overflow. So we will say if two the complements overflows together, if we check. So we can use that by the ending when we compare it so long or like the bytes or word version. So we just change the last one. So it's kind of similar concept when we like move. And then for the test setting condition, so with the test instruction, so for the test like with the long, then we're testing like compute like B A and B together, but without setting any destination. So we set the destination code like just mainly based on the results. And also it can be like useful. So when we have like maybe one or operand to mask. And also sometimes when we need to test it with the 0 or like maybe just like positive, we can do it in this way. Like test it in two register. You need to pass it. So if we set and then it's a zero flag, then we can like say, okay, when it's like together they equal to 0, or the sign flag, okay, less than. So you see the kind of like patterns. So refer to this one. If we need to check it like compare condition, then maybe we will have something carry will be the CEF, the curve fat. Okay, fat. Okay. So if we check something values, if they're equal, 0 fat, or we're checking the sign fat if we are like minus and less than the value, so we'll be like have a sign. Okay. If we checking for the overflow, we'll be using overflow fat. Okay. Like this. And just mainly we checking if we are for equal. Okay, for the equals, like in the previous, we just are loading the value to the register. And if we want to like compare if taking the example right here, if we are compare x and y, so maybe like we try to check if move the value right here from the register. Okay, so if they are not equal, then they will like, so they will move and then they have a call and then they will jump to another like location. So if they are not equal, they will just like move it like this. So it's a message from the register customer. And how about the loops? Like we talk like in C, so we have the factorial function, and then like when we pass the value, then we have the do while loop, and then every time we like times by x and x minus 1, and then like this. For the factorial, like we change it to our assembly language. So after we adding the value to the register and move it, and every time maybe. So you right here you see we have different type like reference like of the on the our register address. Okay, and then moving, and then we giving a loop, and every time we just like decrease it, and we will try to like doing the comparison CMP right here and checking the condition. If no, then if we jump back to L2. If no, then we leave our loop like this. And for the C language, one more time about the switch statement. So we have some like if we pass a variable and then checking like for different case, okay, and then for different case we will execute like certain statement. Okay, so right here. And for the implementation, so the options including some like serious conditions. So for the test long, maybe should be like follow with jump equals. Okay. It was if okay, that means that it maybe there's some few case or large range of value. But if we have so many cases, so it's getting more slower. Okay. Because we need to like checking more like all the case one by one. And for the jump table, we need to look up for the branch like target. So right here. So when we need to like for different case, we need to jump to certain position. So if possible, some like small range of integer constants right here. And if we start with the L3 table, like right here. And then maybe if we need to get the address, like where should we jump? Maybe right here, like +4 times X. Then we need to jump to it, that location. That's how it. And so we need to like pick some like information based on their structures. Here will be the like complete code, including the value result, and then have a switch condition, and then for different case, and then we will execute certain statement, and then break. So we'll complete the switch. When we break down to the assembly language, including like some sessions, some data. So we'll look at, okay, for the assembly, we'll see we have the switch condition, like let's say L10, L4, L5, and 6, 8, 9, 3 right here, and for different operation. And L10 right here. So it kind of like similar idea, like it telling, okay, what the jump tables, and I think the location will be this part long, and L4, L9, okay, and then L5. So all those like will be the keys that jump the table, maybe like in L10, like maybe another one right here. So the array of the pointer will jump to the location. So initial to the X will like this, like in the beginning depends on the X. Will look like this. So for this, like we try to avoid some like conditional branches. So in the modern CPU, so we have the kind of deep pipeline. So those like instruction will fetch like find advice like in the execution, and those masks like will be cause the latency go to the memory. So then we need to think about like maybe what if we hit the conditional branches. So we need to like predict maybe which branch to take, and then to speculatively like fair to execute, and also some branch prediction in the CPU. So the next, but also we need to avoid the conditional branches like altogether. So in the mechanism, they try to maybe doing the instruction prefix. So the REP, repeated, or like search condition SCA, or some conditional move, C move, and also like put some condition execution into the data path. So instead of the control path, or include some like extra readings, so they do not need to use for the this class. So that's how we can like try to avoid the conditional branches. And for the functions, we the call like call, so we can like handle based on the calling conversion used by the processor, or also the compiler. So it really depends on the hardware. And right here we will see, let's say the CS 201. So if we are using the like 86 and 64-bit, so you see sometimes we mix together. For the first 6 integer parameter, so we pass in, and then we have some additional parameter we pass on the stack. So this one using, and if the class using for the 82 will be like 32-bit, then all the parameter will pass on the stack. Here's a slight recap. When you ask like what is the stack, so it kind of like when you learn the operating system, so part of it. So it will be the region of memory. So managed for the last in first out discipline. Okay, and they will start with the high address, and then they're going lower address on the IA 32. So and then the register ESP, so indicate the lowest stack address. So we know the also the address of the top elements of the mechanic. So we'll keep increasing when we the stack will going down, and also the address like will going up if we are stacking more and more. Like maybe the statement, okay, if something loading data like into it, so we'll be like saving on the stack. When we try to like pushing like in the stack, that means we try to, then we will like decrease the ESP by 4. So right here, and we will try to like fetch the operand from the source, and while the operand at the address like given by the ESP, so we can adding it. And it can be using another way like subtract and move. So like subtract, because like we have the decrements by 4, right? So we subtract the ESP with the ESP by 4, and then we can move it move along, and then the ESP location. So it will be like this. So it's kind of like similar way. And for popping, okay, popping, that means we're taking from the top. So if we need to like pop it from the destination, so we read it from the ESP and then write to the destination DSD, and then we increase it the ESP by 4. That means that we are popping up. Okay, so same idea. So instead of using subtract, then we will move it out and then add 4 back to ESP. So here's the idea. Because we are going like, if we are adding more value, so we're adding the pointer like going down. Okay. And then the stop bottom, the new items will be right here. And if we pop out the item, then we need to put it back. So this time we're adding. So here's the idea. And here's the operation example showing, okay, if we looks like, just like in certain stage, if we have something right here, 1, 2, 3, and then if we try to push, if we try to like push our value the source, okay, so we add it right here, and then it goes up top, and then if we pop out, then we will move the tool right here, the location. So here you see, we have the register EX, EXD, ESP, and for ESP is the stack pointer. So we will try to remember. So in this moment, because the with the initialization, so the ESP is keeping the 108 right here in this moment, right? And maybe in the register later we have a value is the 213. Okay, so if we try to push the EX, then we try to let plus 4. We will try to minus 4, so it goes down, and will be 108, and then we'll minus 4, and right here, so the new ESP will be 104, goes down. Okay. If we try to pop, then we need to add 4 back, right? So right here, so move 4, and this time the ESP will change back to 108, and maybe still because when we put it to EDX, and EDX will store our value, and we'll go back. So but right now, because we didn't change any value on the EX this register, so we are not change anything. So it's how it looks like. And we have the procedure course, and then we have for the procedure course, we have the control flow, so including, so we will like push the address of the next instruction on the stack. And sometimes like if we have like go to a certain label, then we jump to that label. Okay, so those like procedure returns like return, so they will pop the address from the stack into the EIP at register. So here's the one of the example. If we have the like initialize the we have the 108, and then suppose the next one will be 104, right? So we know the ESP is pointing to the current one. So the top, okay, 108, and then the EIP. So the EIP, that's what we say. We say right here, the register we're going to pop out. Before will be kind of like will be 8248 54E. Okay, and then if we have a call like 8448B90 90 next call. Okay, so we got next one instruction. So because if you remember, when we are called, it's the same idea to push something, right? So if we try to push something, So we try to like move our the stack pointer ESP. So right here, like same idea. We move our pointer down, so we save the value. But because the EIP, so it's like return. So we save the port the EIP register to the value which one we got to jump. So this time will be say if we want to call, so 80 for the HB90, then we put it to the EIP. So which one we're going to call. So here's the idea. And for some procedure for the return. So this time, like if we need to return it, so we stay on this stage will be like the latest for the top is 104, ESP point to 104. And then maybe if one of the EIP we store is like 90. And if we try to return it, then this time we will just like, okay, this time we'll go back. Okay, so it's like popping out. So we're adding like 4 bytes go back. So the ESP will becomes 108. And because we try to like pop it out, so this time we save it to return. EIP will be the one store on the 104 right here, the address location. This is how it looks like. Okay. And when we have the procedure called control flow, so it's a call like let's say we have a procedure like foo right here, and then try to call who. So who is the caller, and then who is the callee, and then the control will be transferred to the callee. So like if we have a full function and then we call it, so we execute. If we call another procedure or like other function calling it, then we will like execute this part. And after we complete the child, like the procedure, then we will after they able to return it and go back. Okay. So when they the procedure returns, so the controls like transfer back to the caller. Okay. So every of them like will be in the order will be last in, first out. So that's why it like naturally implement like for the stack. So the reason why we're using the stack like this, like the structure, will be used for the procedure call. Okay, and those like the procedure calls and the stack the frame. So you see start from the stack bottom, so they will keep like going right, going down and then staggering together. So we need to know like how does the callee know like when to return later. So they will always have like address pasted in some like well-known location on the stack. So within the stack frame, and how can they like pass some arguments? So you know like when we try to pass the argument, so when you're writing the function, maybe like when you learn C++, see some examples like or other function, similar idea. Then how can we pass it to the callee? So they will some also they can paste in some well-known location on the stack. So within the stack frame. So they're all like under this like some like stack frame. And upon those like procedures invocation, so those like stack frame can create for the procedure. Also, they will like push on the program stack. So right here we like keep going. So you will see, okay, so when they going down and then when we like popping up, then we'll have a chain like step on foo and then who am I like this. So for the return procedure, so when you did like pop off the stack, then the caller stack frame is recovered. So when we like pop up one, then we can like call that. This is how it looks like. And when it like keep on like track on the stack frame, so they'll like stack pointer ESP, so they'll move around. So you see the ESP. So every time like when we like push like pop the statement, so when you every time run a statement, so they are moving around. So they will like will be changed like within some procedure. The problem is okay, how can we consistently like find our parameter and function argument? So maybe we need to have some like base pointer. So that one the EBP so it's using. So they will call the frame pointer. those like pointers will point to the base of the current step frame, and within each function, EBP will stay constant. That's how it works. So if for most like information on stack, they will reference like relative to the base pointer. That's how it looks like. And then the base pointer will set up is for the programmer's job, like depends on you. Sometimes like actually it would be the compiler help us. So when you run the statements, and then when we build a frame of the function right here, like from, and then we have the ESP set pointer like moving around, and then the EBP with the base pointer like moving within it. And you will see the step frame, so including, so right here maybe the caller from the beginning, right? We have the caller, so we have some maybe have some certain functions and arguments that are built, and then we have the return address. And you will see we have the frame pointer. Okay, we have the next one, and then step pointer. ESP is right here, because it's going down for low address, and including some like some old EBP, and then some like set register local variables that stay right here. And this yellow part, so includes the O-frame pointer, and then save the register context and local variable right here, and then see some parameters for the function to be called. So maybe the other functions. So it will like keep building the stack, and the ESP will like goes down, and then the frame pointer will change because we save the with the EBP. So same idea. So they will like push like in the reverse order the parameter. So they will, the last parameter they will like push first. So that's how it. And another function use your idea as swap, because we will like try to change the values, right, between two variables. Okay. So when we call this function like calling swap, so they will call like swap right here. So we will maybe here is the global variable in the beginning. So we have like two values like push in. So we save a value, and then we'll call the swap. So right here, so we have the step. So for the this stack, maybe we are like trying to create a pointer T1 T0 T1 with their pointer address, and then we just like change it, okay, in reverse order, and it's okay. And for the swap function, because we're calling this from the call swap, and then we will have a column will be right here, and then the call grab the two zip1 and zip2, right? We passing the actual their address. So when we call it and pass it, so right here, so we add one more stack, and then we have their variable with pointer, and then giving the return address. So will be the ESP right here. So will be a stack pointer with the last one. So after we complete this stack, then we will like pop it out, and then we can go back to the caller frame, and then complete the rest of it. But because it's just like done, then it just like return. So it's nothing. And start with the beginning. So you see like for the calling the passing the first, we for the second part, we need to move it, push it to their own register. And then for the body right here, so they were like changing, assign, okay, they'll register the location, so this is moving, but going. And then after they completed, finished it, then they can move it, pop it back. So you see the EBP base pointer, so move it by 4, and then from the EBX, so we didn't mention it, but you see like after we complete, so from the EBP, the base pointer, and then from the ESP, and then we just like pop it up. So we do not need to keep it. So right now, then we have the new ESP just like coming back. So it will be like this. In the setup stage, in the setup stage, so you see like maybe we enter, we have the EBP, so it's the base pointer, and ESP is after we add the values over right here. And if we see like after we complete, we have the YP XP. So you will see the YP XP, the source code. Like when we pass it value and we give, so we give we'll save it that the OEPP is the base pointer, right? So and then we have the, after we push this one to the stack, so the ESP will save it. So we first day we try to like for sure we first day push the EBP, and then we will move the ESP to the EBP, and later we will just like push the value back to the EBPX. So go back to a value, and another one for the 2. So the stack, like if before the instruction, just go back. We this time it's the YP. So when you see it's like moving from the ESP to the EBP. So this time the ESP and save it to the EP, BP. So they're putting right here. So we'll be the same. And then last we push the ESP to the new one. So we will like save it. So this one will be goes down. So here will be the total like 3 steps. Like when we try to moving the stacks and from the OEP base pointer and then adding the new ESP. So always we need to like push it. So you just like return to the process, start from our first one. So we need to like push the EB to the new one, and then we will move it in the second step. We'll move the ESP and then with the new EP, and then later we will push it. And we will like add it, then the new ESP will be the new content. Okay, so we will save it. So this will be the final result. How this how it looks like. And then within the body, so referring to the EBP. So within the EBP, you will see because we try to like getting the reference address and passing it, and you will giving the offset, so relative to the EBP. So this one depends on the code. Like of course the compiler we have a like say okay, start from like 12, 8, 4. So start like 12, 8 right here. Before will be the return address, so we just ignore. So start with the 12. So they will like this one try to get the YP. And then for the 8, from the like the base pointer, and then get it to the one is the for the register ECX, and the next one will be the EDX. So they will get the 2 values like YP and YX. And after we getting the value, of course they will try to push it. So the from the EAX, so like E6 goes in, and then we have the EDX to the EBX, and then we just like move it. So they will switch it from the like EAX and also EDX. So they will just like, because when we try to swap it, so we always need to create the extra we need to have extra address, or you see the variable. So we're using the extra registers to help us to like temporarily store it and then put it back. So we use the move. And after we've finished in the steps, like after we like complete it and move it, then we need to like let it to go back, right? Because that's rubbish. And then we need to first like we will need to -4 from the we need to from the our EBP and -4. So we'll go back. So we'll be getting saved to the EBX. So we'll move it our EBP of our like ESP. Okay, so because we need to like put yes, and then we can like pop it out our EBP. So the pop function, so we pop it out. Then after we complete it, then we can just like go to return address. So return it and then go to previous location. So here's the line, and then next one, you will see the pictures. So in the after we -4, we just like go to this stage, right? And then we try to move our ESP. So because EBP, let's say for the ESP, so right now will be the same. And when we move on to the step 3, so we pop it out. So when we pop out our EBP, because the EBP like on. So once we try to pop it, and then we have a new ESP. So there will be the return address right here, and then go back to the step. And then with the last step, so you see that once we return, and then we just say end the whole stack. And once we end the whole stack, then we suppose we will jump back to our caller, the of the report. So kind of like leave it and finish. So you see all the steps. And all this, like you see, when the local variables, so you see the relationships, the relation between the EBP, because you see they will store it above the EBP. So because the EBP always we save in at the lower address. Sometimes we have that showing like -8, -12. So it's like reference address with referring to here. So if you see the EBP minus the values like -4 and before right here. Because when we try to add the value, like we move like 12.8 right here. And then when we move back from the old EB point, then we need to like minus it and go back. Like goes down. And how do they like preserve like if the current function from another function? So they will the compiler will update their ESP, so beyond the local variable. So before the issuing code, so maybe they subtract it for long like 64. So it's the located like for the ESP. So for the compiler, they may be allocate like both some local variables and some like space for the parameter on the subsequent call on one location, so they can maybe like reserve something. And if what happen if some have like if the current function but the returns, so they will all lost because they're no longer weighted. So once the ESP right here, like in case they just like jumps back, let me see that. If they have the ESP, so if we have some local variable right here, so because you know the local variables on the function, there all these will be, even though they are like using the reference address, but they're created as a local variable. So in case they have a return, then they will all lost, so they are no longer valid. So we think all those like vectors, so we maybe like use that for the temporary storage. So like including the conversions, including the caller save. So they will save some temporary inset frame before they calling it. And also, you know, the frame actually same idea. So if the caller have a save also for the call E, so also we will like save the temporary. So in frame before using. So it will be same idea. And for the vectors, the usage, including for the integer vectors, that we have two special use, like including the EBP and ESP. So you will see a lot for these two, for the baseline pointer and so the stack pointer. And also we have like three managed as a course save. So when we call a course save like temporary, so we have EBX, ESI, and EDI. So if we have some old values, so they must save on, then they will save the EBX, ESI, or EDI. So kind of like, but they have the stack have a parallel to using. Okay, and also we have the caller save. So when we say the temporary, right? So we say that a save like temp And for the caller, we including like EX, EDX, and ECX. So will be so but just do what you please, but they expect like any call you to do so as well. And then later when they will return a value. So in the EX, like this, that return it. So you will see for the step because we have the caller, right? Caller, and then they will call have a call e function, and then they will save it, and all the register command like start from EX, EDX, and ECX. And for the call e, EBX, ESI, EDI, and we have the special use the EBP for the frame and the over and then ESP. So here would be the old register we're using. And here's the one example, like if we're showing return value in the EX. So that's why like when you're writing the assignment language, sometimes you see when we try to return the value, right, like always saving in the register EX. Or like we try to return the value in from EX, that's how it looks like. So when we like return, when we have a function, pass the parameter and return it like after we pass one. So we pass the value to the EX, and then after edit, so we will like pop the EBP, the base pointer, and that's it. Because because we have the base pointer because we try to edit, right? So create the frame like this, kind of like the for the EBP. So we will try to like push it and then move the ESP, and then we will like add the value from the base pointer like 8.8 from the EX, and then we add the value +1, and after +1, and then after we complete the step, then we are done. So we can like pop it EAP and then return. Okay, so we are done of the step. And right here for the management, including the arguments and then the local variables management, they can like different. So it really depends on the compiler and source code being compiled. So if you ask if they are equivalent, like we try to like push the EBP, and then also same like when we try to move the UV like the ESP included, and then next we try to push it. So you will see the like when you the two contents like local, so will be slightly different. So we have the EBX, right? Slightly having like what's the EBX? EBX, the core E register, and we try to add 8 to the EBP from the base to a EX, and then we push that to EX. This is how it looks like. And maybe in other like compiler, maybe slightly they're doing another way. So we have the ESP, and then we try to subtract the ESP. So we move the ESP and from the ESP. So we add the like value 4 and then to the EBX. So you see like same, but we move the ESP and then EBX. So after we complete, then last step, they will also like move the 8 like from the endpoint to the ESP, and then they will call the printf. So it may be like looks like the steps looks not different, but they will like this doing same. So for the multiple like C conversion, so they can be like compared with the difference like between like if they're fast or standard or like so seeded, and they will be slightly different in like caller safe or the call e safe. So when they try to pass the parameters, and if they want to have some like shortcuts, then maybe the EBP, the base pointer, so the omission for the simple caller, and for the C purpose, then they will use ECX as a this pointer. So if you see the sometimes we will have a this like if you create a function for this, then ECX will save the this that you referring to, and then they have a called a V table. to implement the methods. So a V table is like virtual function table. And the functions, they have like for the frame setup kind of like various. So it will be like we have a dummy byte in the Windows XP SP2, so they support the hot batch. So you like they put it like long time ago. And the window like structure exception and handling, it would be the FS register. So the linked list of the function they will start like store in the like exception frame on the stack for the error handling. So we'll be like doing this way. And for the library, those like library, so we're calling the library C to perform the IO, and also the format IO, so with printf, scanf, so they have a format output to the standard STD out or like format input from STD in. And also we have the formatted IO, so including the push gas. So they will output the string to the SD the out standard out or like the input string standard in, that is. Or we can check the using for the string operation, so like string length to get the strings like length, also like strings CMP compare, so we compare two strings. When we try to use the function like let's say the printf, so the format output like in and then printf function, and then we'll try, and then we have the refer to address like format string. So we will send the standard output to standard out. Also we have other variant including the fprintf or sprintf. So each will be like send the output to a file or the output to a string. And also we have the return value, so they will be maybe the number of characters print. Okay, but they're not including the training. Okay, on the error if some negative value is returned. So this is like what the printf. And the function like format string, so they will compose like of the characters. Okay, so they will copy some unchanged like into output, and the format directive specification including the character C, S for string integer D, unsigned integer U, hexadecimal integer X, and they also like can be used with the specifier to determine the length. Like let's say string only 8 characters. So they put the H right here. So therefore, it's important for eliminating the buffer overflow. So that's what we're using. You see all these like example we are using, like showing is more like in C language, more lower level, compared with the C purpose. So especially for those like we say slightly lower language, because really rely on the like compiler, it looks like different. And right here will be the example. So depends on how familiar with like with C. So you say same with the main function, but the arguments array, and then we create the variables right there and then put it out. So when you pass like when we have some something like D, X, D, U, S, so just refer like okay, if I need to put it out as that integer or like hexadecimal integer, and also like what's their unsigned integer, and then how can we output it as a string? Okay, like this, and then this one will be the passing. So A6, A, and then B, 255, 255. Last one will be C. So because this one is a char array, but this one also can treat it as the string. Okay, that's how it looks like. And scanf will be the format like input. So we like say the format is pretty similar, and also for the fscanf and scanf from the files and the string. So actually just like kind of similar to our printf. And this one is another example. So just one thing is like pointer, they must be like different to the scanf to store the format input. So they will use like for the CTF like levels to accept the password input like this. So for the one thing is right here for the compare with the printf and the scanf, because when we try to scanf, that means we try to read like from it. So that's why we need to pass it with the address when we are writing the C language. So the pointer is giving to us that value to AB. Like this, after you create AB, then we need to pass the address. That's like is the requirement for this language. So after print out, that's how it looks like. Okay. So just like quickly showing, and then for the and then when as scanf, so they were showing in this way. So scanf we say push it to EX. Okay. LEA, and then they also like I think then push back to EX. So be like this. And so we have the string compare. So we compare to string. So we're passing to string, and then we try to compare, and kind of like pretty similar to the segmentation as the subtraction. And so if they return zero, that means they are equals. Okay. So if it's negative, that means the second string you pass is greater than the first string. So it's positive, that means that the first string is greater than second string. So here's the value. So if you try to compare, so maybe the value password. So if we return is a zero, that means okay, it equals. Okay. So if we returns a negative, that means the second string is longer than okay, or is bigger than the first one. If the second one it return a positive, that means the value is like greater than. So you can see of course you will see that like if the length is longer, the value will be bigger. So kind of like segmented because the ASCII code integers like this. Kind of like almost the end. So we talk about the pointer. So in C, so they will like point to the code location. So we have the call the function pointers. So they will store and pass the reference to code. And also sometimes we use the code dynamic late binding function. So they would dynamically like set the random number generator. So they will replace with the large switch statement for like implementing dynamic event handler. Sometimes the dynamic for the like the GUI, that means that on the buttons, and also the emulating some virtual functions, and also the permission like from the OP object-oriented program. So that we have the Q shot. So they will use with the user supply callback function for comparison. Also the operating on the list of elements. So the maps or lambdas in the function like multiplication, addition, these like. And for the malware, we say leverage this to execute its own code. So all these like using malware, they work on a function pointer. Recap. So if we have the functions and then two functions, we declare right here on the top, that's the structure. And then we have the main function. And for the main function, we will like calling and passing. So if we get the argument, and then we'll execute something, or else we'll do anything, and then we have a call e function, fe. So we see a calling. And right here you see we have a label. And this label is like okay, in case that if yes, then we'll jump. So this one is like called the indirect call. So if you extract right here, EDX, so the code will execute not known until the runtime, because we don't know like which one we're going to run. So we when we convert to the assembly language, you see we will see that because when we move the BP, EBP, the base pointer, so like with the EX, so you know the EX, the low variable, and then we have the FP22, the like EDX, and then maybe we're testing, so we're checking, and then if the jump not equals, then we jump to L4. So if not equal to L4, and then we move the ESP back right from our EX, and we are done. Okay, and then go back if we will call in the function EDX. That's how it looks like. And all these like in our OS. So they're using it in the Windows OS. So it will interrupt the descriptors table, and then the pointers can use like interrupt the handler function or the IDTR XD6 like a little bit will be like just pointer to IDT. Also some like system service descriptor tables, we can use it to point to some like system call. Also we can import some like address table. So those like pointer to the library call. So all these like the malware can attach. And so far will be all these like for this part when we look at the you see the whole lecture right here. So we are looking for is like knowing how the registers like how it increase like because when you learn OS maybe we did mention about like the stack. Okay, when we running certain statement and then we try to like put some in the stack. But this time in this chat, in this lecture, we see that we really dive slightly deeper and telling you, okay, so how the stack pointer ESP, and then every time when we have some including the frame and or like move on or jumping from the one function like from caller to call E, and then how can we return the value, and you see it's like going down, increasing. So that increasing address on top, and then when the stack is always like goes down. So it's the mainly key concept is like if we push, so we need, because it goes down, the value will be getting smaller. So that's why we need to like subtract it, minus it. And if we popping, that means that okay, we are complete certain like function, the caller or return back, then we need to add it back. So it's a pop function, but we are like adding it. So that's how it looks like. And so far, that's it for this lecture. And I know some of you may be still working on the like setup environment, or if you have problem when you try to install the FairyVM, is it normal? You have some lost connection, something denied error message, it's okay. And once you see the background, like because it always like we put in like we start, and if you watch my previous videos, you will see I have some when I try to log in back to the account, and then you will see it doesn't work because you have to switch back to like you have to choose. Now when you see there's a two account, you need to like go back to the first one and try to use the PIN or password. So the one you can log in successfully, that means the correct one. So it will like open the box starter and then complete the following installation. And when you see the check the two folder, when you get things like their complete installation, you see you are able to see more tools available for use, then that means you are doing okay. And about the assignment, what you need to do like complete is the like for the dynamic analysis, that one. And for the last week, I will post it, so make it available and post it on in next week. So I will give you some extra time to do it for the V6 for this lab. So of course, if you're able to do it, you can copy, make a screenshot, like kind of like follow all the steps and try to check, like compare their like hash, and then like try to get their from download the putty. If you remember, I told you like try to download the original one from the official website, and also compare with the one with infected, and then check their MD5, compare the content. Just need to follow the step. But I will post it later. So I try to make the labs slower, then you maybe have more time and the tool you are going to use. So make sure you always set environment. So if you need extra time, if I see I will post it, but if I receive some email saying if you have difficulty to complete, then I will extend the deadline. And if you have no other question, then that's it for today's class. And thank you. Then I start right here. If I
Thank you, Professor.
Okay, thank you. Bye.